Hello everyone. So I want to just say why I think that this is a good time for this discussion. These days there's so much written about data science, there's so much spoken about data science, and yet lots of people don't seem to be very clear about what data science actually is. So I just want to say why I think that this is an important question and something that's worth discussing. So firstly, I think that the profession of data science needs to define itself in order to develop and actually just to survive. So for instance, I run the data science team at a startup in London called Skimlinks. And in common with loads of companies in London, we find it very, very difficult to find data scientists. So there are lots of people, because of this demand, thinking about changing career and going into the career of data science because there's such a shortage, so people are looking for jobs. The problem is that there's no real consensus about the core skill set. So lots of companies are hiring software engineers with no real statistical training as data scientists. I think we need to be a bit clearer about this, and I think that programming and statistics are both core skills. It is a fact that organizations are collecting so much data now that you do need serious programming skills just to manipulate it. I do think the statisticians are the right people to analyze data, but they can't analyze data unless they can actually access it and manipulate it. So secondly, I think that we need to develop some new methodologies. Working on large data sets now is really the norm, it's not really the exception. And I think that many aspects of doing statistics change when you work at scale. So just to take an example, so after running a single logistic regression, let's say, a statistician might run some diagnostic plots to gain a feel for the goodness of fit of the model, look for potential outliers. This approach is just not scalable when you run 20,000 logistic regressions on a single data set, and this is typical these days. I think visualization, hypothesis testing, outlier detection, feature selection, they all require different approaches when you're working at scale, and there's a need for an automated and large-scale approach to the job of the statistician, I think. And it's not just data analysis. Industry and academia face huge problems in the storing and processing of data. Statisticians and computer scientists really need to collaborate to develop this methodology that we need in order to deal with all of the data that we have these days. How do you best foster this collaboration? Should we consider data science to be a new field? Should it have its own journals, textbooks, and university departments? And thirdly, I think that we need to educate people. As I said, there's a massive demand for data scientists, and educators are trying to train enough people to meet the demand. But we're in a kind of absurd position at the moment where every company knows they need a data scientist, but they don't know really what skills a data scientist actually needs. So there are data science MSc programs, and they're starting to produce their first graduates. Some of these courses do not contain a single statistical data analysis course as part of their core curriculum, while their courses can be dominated by big data frameworks. I think that new graduates from these programs who are trained in a hot big data framework are going to be shocked when they discover that industry has moved on by the time they graduate, and they've moved on to the next big thing, the next big software framework. And there are those who say that data science cannot be taught in an OSV program at all. I'm sure we'll have some opinions on that. So I'd now like to introduce the panel. The panel are actually helpfully sitting in the same order as the brochure for the event, which makes things easier. So we'll start on the left.
Rogues gallery. Yes.
So I'll just introduce everyone very quickly. So at the very leftmost end of the table from where I'm sitting is Chris Wiggins, who's Associate Professor of Applied Mathematics at Columbia and Chief Data Scientist at the New York Times. David Hand, Emeritus Professor of Mathematics at Imperial College and Chief Scientific Advisor at Winston Capital Management. Francine Bennett, founder and CEO of big data startup Mastodon-C. Patrick Wolfe, Professor of Statistics at UCL and Executive Director of the UCL Big Data Institute. And Zoubin Ghahramani, Professor of Machine Learning at the University of Cambridge, who was recently elected as Fellow of the Royal Society. So I'll let the panel introduce themselves. Chris.
Thank you, Martin. Good. So I'll just maybe spend 5 minutes on my relationship with data science. So my background originally was in theoretical physics. I started my PhD in the early 90s, which was a time of great interactions between physics and biology, mostly around single molecule biophysics and trying to find individual problems in biology that you could make simple enough that you could apply physical modeling to them. And it was a very exciting time to be in biology, not because of that field, but because while I was working on my PhD, the first freely living organism had its genome sequenced. This was Haemophilus influenzae in 1995. And so I got to have the experience of starting my PhD at a time when biologists found theory sort of curious but not particularly useful. And by the time I'd finished my PhD, biologists really, really wanted to collaborate with anybody who knew how to make sense of data. And so by the time I'd finished my PhD, it was clear that the questions that were of interest to me about how to think about biology had actually become statistical questions. And my research over the last 10 or 15 years has been in what I would call applications of machine learning in biology to biological sequence data, biological microarray data, biological network data. And that has been very revealing to me about how the pain points that biology went through when suddenly biology found itself awash in data were repeated in other fields of human endeavor thereafter. So many fields now find themselves having centuries of expertise and knowledge about the way their field works, and then suddenly finding abundant data and not having some sort of obvious way to connect those data with some sort of fundamental model. And in particular, one of the places that I've seen it is more recently in working with people at the New York Times. So as of about a year ago, I split my time between Columbia and the New York Times. At the New York Times, I've been building a data science group to try to address how best to learn from the data that the New York Times itself produces as a company in the working of the New York Times. So we have abundant data about the way people interact with the product, primarily the digital product, as well as the full content of the articles, information about who subscribes and who cancels their subscription, logistics information about how many copies of the paper are sent to and purchased at all these different stores. And just like in biology, a very complex system, people who have worked on the problem for centuries and have a feeling for how the complex system behaves, and then abundant data that it's very challenging to try to learn from and reconcile with this domain expertise. At Columbia, I've also been involved in the creation of Data Science Institute, which launched a few years ago. That institute is pan-university, although closely aligned with the engineering school. And we've created a certification in data science, a master's program in data science to speak to Martin's concerns. And so it's been a very intellectually exciting time to work with people from all these different disciplines of the natural sciences as well as industry that are trying to make sense of the world through data in a sort of a set of pain points that I would call data science. Thanks.
So, for 25 years I was a professor of statistics, and then Imperial decided to make me an emeritus professor of mathematics. For 25 years I argued that statistics and mathematics were different disciplines, and now I've sort of decided, if I haven't convinced them yet, maybe I can convince them from the inside. But I'm a statistician, so from Imperial College. I'm also, as you've heard, Chief Scientific Advisor at Winton Capital Management, which analyses very large data sets from a wide variety of areas, obviously a lot relating to the financial markets, but also many other areas. I'm also chair of the UK's Administrative Data Research Network. What this does is link data from all government departments to enable researchers and people investigating public policy to carry out work to develop public policies, explore public policies, and for social science research. My statistical interests, so I'm a statistician, but my statistical interests, I'm sort of very much at one end, I think. My interests overlap things like data mining, machine learning, and related areas, many of which I consider subdisciplines of statistics. Machine learning is clearly a subdiscipline of statistics. I took an MSc in a statistics department, but then I took a PhD in an electronics department, which shows that I have an interest in these areas. And in fact, as well as having written many statistics books, I've also published books with titles like Principles of Data Mining, Artificial Intelligence and Psychiatry. For 10 years, I worked in the statistics department at the Institute of Psychiatry. artificial intelligence, frontiers in statistics, AI and computer power, the impact on statistics, and so on, pattern detection and discovery, so on. That's me. I'd like to make a few sort of fundamental points about my perspective on data science, statistics, and so on. And I want to begin with a point that I've made before, you might have read it, that people don't want data, they want answers. That's key. Data have to be supplemented by the skills and techniques to enable people to extract meaning and answers. And without the statistical, machine learning, data mining skills, we have nothing. Putting that another way, data aren't the same as information, and a very nice illustration of this, which I'm sure you've come across, is how the number of pixels in a digital camera increases as the years go by. The amount of data constituting each picture certainly increases, but the amount of information doesn't. My second point is that there are two rather different kinds of data challenge and opportunity. You've got to say, whenever you say challenge now, you have to regard it as an opportunity. One relates to data manipulation, so sorting, aggregating, searching, matching, concatenating, all this sort of thing. And examples of recent innovations based on those sorts of things include automatic route finders, apps for bus and train status, tools for identifying a piece of music. They involve those sorts of algorithmic exercises. And I think the challenges there are fundamentally mathematical and computing. The other kind of data challenge and opportunity relates to inference, using the data that you've got available to make a statement about some other data set or some other more extensive population, or perhaps what's going to happen in the future. So in medical research, our aim isn't to draw conclusions about the patients we've got in front of us, but about the next patient who comes through the door, about future patients. In economic forecasting, we're not trying to tell us what the data say in the past, but what it's going to say in the future. And very clearly, for that kind of data exercise, opportunity and challenge, it's very statistical. That is statistics. I think it's so obvious it doesn't need saying that statistics is the core discipline for that, whether the data are big or small. In some cases, these two kinds of data challenge, manipulation and inference, come together. So in fraud detection or face recognition in crowds, for instance. But I think it's useful to distinguish between them, because if you look at people setting up startup companies, you can come across people who very much fall into those two different camps. I'd also like to make the point, and this is crucial, all data sets have problems, distortion, missing values and so on. Data quality is a key issue. Obviously, it's been well explored for small data sets, but it's even more potentially serious for large data sets, because necessarily the computer is an intermediary between you and the data. You don't see the data in the same depth you do as with small data sets. The description n equals all is sometimes applied in the context of administrative data collected as a side effect of some administrative exercise, and I think that's laughable. That, okay, there isn't sampling missing data, but there are other sources. Oh yeah, I'm sure most of you have heard the assertion that we no longer need theories. We can now just look at the data. But that's true only in very limited situations, which we can talk about afterwards, perhaps, during the question time. But I have many examples of where ignorance of theories, just looking at the data, has led to mistaken conclusions, in some cases quite serious mistakes. And I'd just like to end, because big data, this phrase, which I really don't like, and which many of you won't like, I'm sure, is so pervasive now. I would just like to stress that big data doesn't mean the end of small data. And I can prove this mathematically. You give me a big data set, and I can split it up into lots of small data sets. So there are more small data sets than big data sets. That's where I'm going to stop.
Thank you, David. Fran?
Okay, thanks. I have to confess being slightly terrified because Principles of Data Mining sits on my desk at work and looks back at me every day. Just connected the hand of that and the man
You're
sitting
going
here.
to turn it around and face the other way.
Yes. So I daren't argue now. So my name is Francine Bennett, and I am from a technology company called Mastodon-C, and we build and run big data systems, to use a tricksy term. So we use recent advances in technology to analyse either very big or very complex data sets in ways that were prohibitive to do before. And I've come to this field in a bit of a roundabout way. So I was a maths undergraduate, but really only pure maths. So I wasn't actually a lover of stats at that point. Started a PhD, dropped out, and became a strategy consultant for a few years. Got very, very bored of drawing PowerPoints, found not much intellectual challenge in that after a while, and moved to Google's strategy team. And from there started trying to solve problems with other tools than Excel, started hanging around with the engineers to try and work out how I could make data do what I wanted it to, and sort of rediscovered my maths brain from there, and had some hasty catching up to do on the stats side of things to work out actually what could I claim about data. And from there I realised that the technology that we use to deal with data has moved on so much in the last few years, and the computing power is so much more available than it was a few years ago, that applying things like data science techniques, or even just very simple data processing techniques, to a new field of problems has become possible, which has led to the whole data boom that we're looking at right now. And have actually found now that there's a very interesting niche for companies like us who actually want to apply these tools and techniques to problems that we find more interesting than things like advertising or banking, which, interesting though they are for a while, I can tell you after a few years of trying to get people to click on ads more, the intellectual stretch of that, it just doesn't start to make you excited. So we now work a lot more in things like the built environment, in sustainability, energy consumption, that kind of area, where there's a whole new emerging field of data problems. So as the physical environment becomes more instrumented, new data streams come in, we have new analytics to do, and we also have new software engineering problems where actually the data comes in more quickly, so it's not just finding conclusions, but it's the speed of performance is also a very important part of the type of work people like us do. And this brings us to a really interesting place, I think, where I would say a lot of what we do is a combination of software engineering and data science. It's very rarely actually pushing the bounds of statistics, so it's often pushing at computer science a lot more. But a lot of you will have heard this said already, and it's sometimes used as a put-down, but I think there's a lot of truth in it, is that a data scientist should be someone who's better at stats than a programmer, and who's better at programming than a statistician. And that breadth really is the cost of entry, I think, to this kind of field. And that breadth is actually more useful than depth most of the time for a data scientist. So yeah, I think it's a very interesting time for people with those breadth of skills, and with the communication skills to actually get their solutions implemented, which I think is very easy to forget and is actually critical to making things work.
Thanks, Fran. Patrick?
Yeah, thanks, and it's a real pleasure to be here. I'm Patrick. Nice to meet everyone. I'm looking forward to chatting some more, and it's a great panel. So I think I've already heard some interesting perspectives. Let me just tell you a little bit about my background first. I've seen data science, or whatever we'd like to call it, from sort of several different perspectives. So I started out life as an undergraduate in electrical engineering because I was told that had the most mathematics in it, but also in music. So I studied both of these subjects for a while and ended up doing a PhD that kind of combined them by looking at ways to model speech and music signals and noise processes to kind of restore old audio recordings. So I kind of gradually realized that my primary intellectual interests were very statistical in nature. Building statistical models, understanding data. And so I've gradually kind of moved away from my electrical engineering heritage, but I've always maintained one foot in an electrical engineering computer science department and another in statistics. So that's kind of really informed my perspective around data science, and even today I have a primary appointment in statistics with a secondary appointment in computer science. And as was mentioned, I'm the executive director of our Big Data Institute at UCL, and I'll tell you a little bit more about that later. But that kind of brings us up to speed on where we are today in terms of my background. My personal research interests at the moment are about networks, and networks are clearly a very convenient way of representing or summarizing certain types of very large data sets, particularly if we're mixing structured and unstructured data. So my kind of mathematical interests at the moment are really about how do we understand the behavior of large networks? How do we model them, summarize them, draw defensible inferences about them, and generally kind of build mathematical frameworks that allow us to talk about large sample statistical properties of network inference. So enough about my background. There's kind of three things I'd like to submit to you for consideration, or 3 points I'd like to make. The first is, I think from an academic and intellectual perspective, this is a once-in-a-lifetime opportunity for all of us. I think that there is a very, very unique and real opportunity here for statistics to participate as a discipline in a real change of paradigm in the way that we think about making sense from data. I don't mean to suggest that everything old is useless and everything new will be exciting. I'm much more a subscriber to the philosophy that there's very little truly new under the sun. But clearly the paradigms under which we collect and analyze data are beginning to change, and I think it's incumbent upon us to recognize that. So that's one point. The second point is about what it will mean to shape the future of data science. And I think for that to make any sense, we have to identify, recognize, and nurture an intellectually coherent core. To my mind, that core lies at the intersection of mathematics, which is about structure for understanding problems and abstractions, statistics, which is about developing tools based on that structure, tools to enable inferences that are defensible, repeatable, and actionable. And then finally, computer science, which is very much about systems and scalability and allowing us to actually implement the tools that we as statisticians develop from mathematical theory. So I think I see those three areas and their intersection really as the intellectual core of data science, or whatever we choose to call it. And I'm leading our Big Data Institute at UCL in a direction that is all about kind of nurturing this core and building it out. I think in the best case, there's a real opportunity to connect people in this intellectual core with this expertise, with all kinds of people in different application domains, whether it's physical sciences, whether it's biological sciences, whether it is various industry or public sectors. And I think in the best case, real problems feed back and stimulate the core, and the core is responsible for developing abstractions that can then filter into these application areas. So the last point I'll make is just that for statistics, I think the most important thing is that we recognize the following paradigm shift. What most of us learned as undergraduates are the types of techniques that were designed when data were rare, expensive, and every experiment was explicitly designed in advance. Right? So designed experiments with small data sets. These days, everyone wants to work with what I would call found data, which is to say the data you didn't necessarily set out to collect, but that you happen to have available. It's very intellectually appealing to think that we can augment a designed experiment, an amount of small data that's carefully collected and very precise, with lots of found data, right? So maybe we do a small census sampling and we take lots of other sources of information and we augment. It's this responsibility of our academic community of statisticians to help people do that. Right now, we're still stuck in a mode of teaching people in traditional statistics programs how to work in the old paradigm. We have a responsibility to develop new methodologies to allow practitioners to understand how to draw inferences in this kind of new world of found data. And we can't afford anymore to be the community that always tells people what they can't do or shouldn't do, or why they should have collected the data differently or designed the experiment differently. We have to deliver methods. We have to deliver methods that allow people to make sense of all different kinds of of collections and scales of data in ways that are intellectually defensible. So having said that, let me pass it over to Zoubin, and congratulations again, by the way.
All right, it's a pleasure to be here. I'm Zoubin Ghahramani. I'm sort of an accidental statistician, I guess. I don't have any training in statistics, I have to admit, and you can easily find that out. I started out interested in artificial intelligence, so how to get computers to be intelligent, and also in neuroscience, in computational neuroscience, what is human intelligence. And I couldn't make my mind up between these two fields, so I ended up getting a PhD in neuroscience and worked in that sort of area. But I was ultimately interested in making computers intelligent, so I dropped the science and stuck to the engineering of making computers adapt to difficult problems. And the sort of in artificial intelligence, at least, there was an old paradigm which was all based around just writing down some set of rules or methods for getting the computer to be intelligent. And that was, in a sense, a big failure. And the revelation to the field of artificial intelligence was that actually intelligence in computers, when you combine it with data, turns into a very interesting proposition where basically the computer's learning from data. So the field of machine learning evolved out of that problem. And then as machine learning researchers, we discovered, well, we need to teach ourselves lots and lots of statistics, because that's the discipline that's been studying how to do inference from data. So I'm an accidental statistician in that my research program now covers things like Bayesian nonparametrics, for example, where I can't really explain it to typical computer scientists, but I could go to a stats conference and talk to colleagues there doing very, very similar work. So what is data science? I think the answer depends on whether you talk to academics or people in industry. I feel like the view within academia is that there are a set of well-established disciplines that relate to data science, namely statistics, machine learning, data mining is an academic discipline, and I would argue also scientific computing. So a lot of people who do scientific modeling, in the applications of science that are very high throughput and data dependent are really doing data science as well. I think if you go and talk to people in industry, they have a very different view. They don't care what academic field you come from. They have problems, and their problems are based around they have lots of data, they want to extract some value. There are lots of very commercially exciting opportunities out of all the data that we're collecting, all the digital footprints that we're leaving everywhere. And the buzz phrases that come out in that community are things like big data, that's sort of made it into the academic community now as well. Business intelligence, predictive analytics, and so on. But it's all about kind of getting value out of data. And I think I don't work principally in industry. I talk to lots of people in industry. And the view I get there is that the largest part of the problem is the collection, curation, manipulation, cleanup of the data. Then there is a small amount of the fun bit, which is the statistics or machine learning. And then there's a large amount of interpreting it, putting together the PowerPoints, presenting it to your boss, or building a sort of system that reliably makes decisions and makes money for your company. Okay, so let's not overestimate our role in this whole pipeline. There's some good statistics and machine learning going on in there, but there's a lot of other messy stuff that we better think about as well, because the risk is we could either just leave it to be completely ad hoc or start thinking about the entire pipeline going from raw messy data to insights. I think there are actually interesting research challenges in thinking about that whole pipeline, something that I've been trying to think about. Now, another point I want to make is that academic fields are social constructs. Okay, they're communities, networks of people who attend the same conferences, publish in the same venues, cite each other, You know, if you're a statistician, you sort of define yourself a bit by who your supervisor was, what department you were in, which journals you publish in. If you're machine learning, you're publishing in conferences, going to different conferences, and you know, you have backgrounds from various different fields. Same for data mining. There's sort of a different community. And I think this is, I mean, partly inevitable, right? You know, science is done by people, and we form communities. But I think it's something we need to overcome. What we need are fewer barriers between these disciplines, and we need more people with the right skills. So these skills are, I think everybody here would agree, statistics is a very important skill. If you want to include machine learning as a superset or subset, I'm happy either way. Programming, algorithms, databases, optimization, visualization. These are probably the skills that are relevant both in industry and also in the sciences or in the public sector. And I think this is an opportunity and also a threat for statistics, because if statistics doesn't move quickly enough, there are other disciplines that are very eager to move into this space. And so statistics needs to jump on the opportunity and try to break down, be central to breaking down these barriers between disciplines and talking to other departments, setting up joint programs and, you know, joint appointments and all these other good things. So that's it. That's all I wanted to say.
So you're right that they're social constructs, but they need to be coherent. So, you know, we can't have statistics become something that's so broad that it has no meaning. And I think one of the ways that you see that become a pain point is what Martin started this whole panel with, which is job descriptions. So when somebody makes a job description, they can't say, I want to hire a statistician, but not a p-value confidence interval type. I want somebody who does exactly this kind of thing. People aren't going to do that. They're just going to make up a new term for it. Now, on a longer time scale, because job descriptions move at a very fast time scale, on a much longer time scale, institutes are going to be created, master's programs are going to be created, departments are going to be created, tenure lines are going to happen, which is a really long time scale because you have to promise you're going to like the person forever if you tenure them. I mean, you can divorce somebody, but you can never get rid of a tenured colleague. So we can't have statistics just say, oh, it's all statistics, right? Because if nothing else, job descriptions are not going to fall in line with that sort of completely everything is statistics approach.
No, clearly everything is not statistics. I wouldn't argue that, you know, sort of
distributed systems,
all these other, you know, optimization, applied mathematics. There are lots of connected skills and disciplines, and I agree that each one of those needs to be coherent. But what we need is interdisciplinarity, or training at least the younger people to have the right subset of these skills.
Yes.
Zoubin, I liked your point about statistics maybe playing the role of the glue or the connective tissue. Something that's interesting to observe, again, from the point of view of how disciplines behave, is that statistics is relatively, in addition to being traditional, it's a relatively small discipline compared, for example, to electrical engineering, which is where my heritage is. Electrical engineering grew up and went through a period where it became much, much larger and much more mature. Right now, you can still go to almost any talk in a statistics department and roughly understand the core basics of what's going on. And in the electrical engineering department, you have people over here who are basically physicists building lasers, for example, and people over here who are control theorists who are basically somewhere between applied and pure mathematicians. So when it comes to tenure lines or hiring committees or seminar series, electrical engineering has become so large that it's split itself into separate subunits. And computer science has done that to some extent if you think about the difference between the system side and the theory side. So one of the interesting challenges to watch the discipline of statistics go through as data science becomes more popular and more important is, you know, how will a relatively small and traditional discipline react to kind of this growth phase, and how will it decide to define itself as it begins to grow past the point where everyone can understand most of what most of their colleagues are doing. And that's just something I think it'll be interesting to see how that progresses.
Comment on what Patrick was just saying. I think statistics went through this, I was going to say bifurcation, but it's a multiplication. There's chemometrics, biometrics, environmetrics, which are all fundamentally statistics, but they have different names, and they've been around for 50 years, decades. But I wanted really to pick up on something you said earlier. I entirely agree that we're in a very exciting phase, and we need new paradigms, if you like, to cope with the large data sets, the fact that data, it's not just that it's observational data have been around for a long time, but with electronic measuring instruments, the data just keep on coming, and so on. We've got to cope with that. But you sort of implied that we needed a shift from the old paradigm, t-tests or whatever, to the new paradigm. We can't afford to do that. We've got to retain the old paradigm as well. We're still going to be called on. You're still going to need to do clinical trials, for instance. So you're still going to need to have statisticians who understand what a t-test is or what experimental design is or whatever. So I think we need to broaden rather than merely shift.
Yeah, that's fair.
I think there's a much simpler issue as well, which is one of communication. So when I work a lot with programmers who are often thinking about becoming data scientists or trying to move into that field, and they're often quite scared off by statistics because they've sort of approached into that area and then tried to gain education in various ways and had it implied that they're idiots if they don't know what a null hypothesis is or if they don't know t-tests. They say, okay, fine, well, I'll just switch to machine learning because there's a lot of rather slightly gung-ho libraries out
More
there which I
welcoming.
seem to press a button and it goes. So there's people skipping past also the fundamentals and just saying, well, that's too frightening, but I can run a neural network, and that's nuts, but that's the way it often is. So I think pushing some of those basics in an accessible way would actually make an enormous difference to the mass of people in this field.
I don't know that we want to say that machine learning is simpler to understand than t-tests, but...
But if you look at the computer science out there and what gets talked about...
Certainly must get talked about, and so...
It's much cooler. It's seen as much cooler.
Well, it's part of our lives. So one thing that's happening is that young people are growing up with Netflix telling them what movies to watch and Amazon telling them what books to read and Google telling them everything. So, at some point students are going to be curious about how this all works, and it's not clear that the core nugget that they need to understand recommendation systems or whatever is the t-test. And my colleagues in statistics have pointed out to me that perhaps we need to change the way we teach the young people because, as my colleague Mark Hansen puts it, the t-test is sort of the crowning achievement of the undergraduate training in statistics, in orthodox statistics. And it's not clear that young people will find that as satisfying as finding out why Facebook is able to figure out what news to insert into their feed and every other way that, let's call it data science, is becoming part of their personal lives, right? As computation becomes more and more personal, data science and algorithms and treatment of data is shaping, our personal relationships and everything else. And I do think that that's going to draw more people into whatever field you want to call it.
Yeah, I think to all the points that have been made, I think we'd like a well-trained statistician in today's world to get a big smile on their face when they recover a situation for which the t-test is the answer, right? To David's point, that you should feel really good. That's become an easy problem, a solved problem. I think the other thing is that, we have a situation where some of the technical tools between machine learning and statistics, for example, are shared. Underlying a recommendation system is some fundamental ideas that can be related back to non-parametric statistics, things like clustering and summarization. You might choose to call building a recommendation system, undertaking customer segmentation or something, but from a technical point of view, it's a pretty core statistical method. But to a point that David made earlier, it's just not being applied to a statistical end. It's being applied to build a box that has good predictive capability, not to understand what drives humans to favor one family of movies over another. So a lot of the underlying fundamental tools are shared, but the jargon isn't, to the point that you made, and that's a barrier. And the ends to which the tools are the means are very, very different, depending on, we're talking about clinical trials at one extreme where life and death decisions are at stake based on evidence, to something like a recommender system at the other end of the spectrum where, or let's say a Google search where what we really want to do is return a ranked list of hits in a way that's useful to a user. A lot of inferential tools there, but the end goal really isn't inference. So I think, as I said, ideally, we'd like to be turning out people who are trained to recognize when the old paradigm or the orthodox paradigm or classical paradigm is appropriate, and when they need to think a little bit more broadly about some of the new situations that we find ourselves in. And I think there's room to do both, but it becomes our responsibility to train people to be able to think in both ways, and then let them decide after they finish their education, in which direction they want to take it.
Thanks, Patrick. So I'd like to take a question from the floor. If anyone has a question, put your hand up, wait for the microphone to come before speaking, please.
Hi. I'm a programmer by trade. I didn't study programming, studied English. But you can just get into programming, and over the years, the experience mounts up, and you end up hopefully being all right at it. So with the sort of experience about trying to get into this world because it's interesting, I've sort of taken the approach of doing some formal statistical training, and it feels very much like you're having to learn 1,000 tiny little building blocks, and it still seems, undergraduate level at that, and it still seems very, very far away from actually doing anything interesting. Whereas, you sort of, from the programmer's point of view, you just jump in, you start using a library, and then, maybe at some point you get interested, how does this library actually work? And you dig in, and you get a bit further and further each stage. Maybe that sort of difference between sort of a top-down from the problem basis versus a bottom-up from first principles basis has got something to do with this?
I think that's maybe largely a function of the way it's being taught. If you are taught statistics through a sort of problem-solving approach using R or something like that, then you're jumping in the same way that you would as a programmer. You're doing things immediately and then learning how it all fits together, rather than learning all the pieces and then seeing if you can build something with the bricks you've got.
Anyone else?
I think also introductory statistics books often will assault you and prevent you from getting to things that are applicable. Like if you pick up a stats book and it says, we're going to teach you a bunch of distributions with Greek letters now, and the appropriate, confidence intervals for all those different distributions, it's not getting you closer to the things that you want to do, which is take a data set of interest to you and make sense of it or learn from it. I think actually machine learning does a good job at this. So when you pick up a machine learning book, it says, here's some unified picture of how we make sense of the world. Supervised and unsupervised, or maybe supervised, unsupervised, and reinforcement learning. I think there's actually maybe more effort to try to take the various ways that we make sense of the world and create some sort of high-level organization there in the machine learning community. And I'm leaving aside whether that's a sub-community of statistics. I think Zoubin's PhD advisor is on record as saying that machine learning is a sub-branch of statistics.
Yeah, he is on record as saying that, but we shun him now in machine learning. But it's okay because he's happy.
I think there is a missing piece of educational material, you're right. So having tried to learn both myself, if you want to learn a new programming language, there's a bunch of sites and resources which will take you through a load of toy examples and make you feel good quite quickly that you've done something, but then give you a whole load of warnings and say, right, here are some ways this can bite you if you don't understand it. So it lets you win and do something good first, and then it'll let you go a bit further, whereas stats will tend to be like, well, you need to understand all of the warnings first, and then maybe you'll be allowed to do something. And there are fewer resources which will actually give you initial wins and initial confidence before drowning you, I think, in the stats world. I'd love to see more resources like that, because I think they'd be wonderful, actually, really helpful.
Yeah, and I think it's to your point, it's the reasons for that are historical and cultural within the discipline of statistics. As a profession, I mean, we are essentially, professionally trained skeptics, right? So it's a fundamentally conservative discipline. Again, the classical paradigm is about being very, very, very careful about what you ought to be allowed to claim about the things you haven't observed, right? So there's almost like a visceral reaction when one sees people kind of freelancing and trying out lots of different ideas. And I do think that needs to change.
And even worse, when they get it done. That must be very painful. when you have a whole book about why you can't do it and then somebody builds it, that must be terrible.
Well, and you know, that point relates back to something that Zoubin said earlier, which is absolutely right. If we already have a reputation as a community of naysayers, right? If we can't find a way to engage, then nature abhors a vacuum, and the doers will be very, very happy to step in. I don't think that that's a bad thing at all. I think that our role is to help people understand what they ought to reasonably be able to responsibly claim from what they've done, and what they need to be more careful about. It's not our role really to naysay, unless we're talking about a situation like clinical trials or public policy decisions that are based on evidence and so on and so forth. But in the world of building boxes and software systems to do interesting things, I think we're historically, culturally primed to be a little bit more negative. And I think that's why the books that you described are how they are. And computer science and machine learning in particular machine learning is so fresh and new that it's able to have a very kind of freeing and creative outlook. And it is part of that, that, I wouldn't call it hacker culture because that's not quite right, but it's more of that problem solving and building and creating culture where you're willing to kind of wade in and get your hands dirty and do something and not worry about whether it's the best thing, but just take a first crack at solving the problem. And that's just, again, it's a fundamental cultural difference in the way that statisticians have been trained to approach problems. But I think it's something that needs to change. I think there needs to be more opportunity for kind of meeting in the minds there.
Question over here.
I'm James Nicholson. I work with a group at Durham University on data visualization, but my background is teaching mathematics and statistics at school level. I just want to make an observation that I'm really concerned about what's going to happen with the A-level mathematics curriculum and the compulsory statistics which is being incorporated into it, because I think a lot of the stories that you're talking about there are actually going to get much, much worse, because the good mathematicians are going to have an experience of statistics which is gruesome and gives them all of the wrong messages. So where they come across statistics or the use of statistics anywhere else, it's about modeling, it's about making predictions, but there's none of that in the course at all. So they're learning distributions, they're testing distributions without actually doing the conditional probability fundamental to it. They're testing correlation coefficients without calculating correlation coefficients. So the logical foundations for what they do in statistics is just bizarre. It's fragmented. It's not there as a coherent, understandable, let's make sense of the world. Now, to me, statistics is all about making sense, making the best sense you can of partial information or uncertain situations. And that seems a million miles away from the philosophy of what's going on in schools. So I hope I'm wrong, but I have a nasty feeling that maybe more people will go to machine learning and so on because the good mathematicians will have such a bad experience of statistics.
Yeah, I mean, I feel that reflects my own undergraduate experience with statistics. When I studied statistics, I was a computer science undergraduate, computer science and cognitive science, but I took some statistics classes and I found it dreadfully boring. I slept through almost all my lectures. I didn't realize it was important to me. It took me years, to suddenly fall in love with statistics. I love statistics now, but I love it in the way that I understand it. And I'm very frustrated at that experience because I lost a few years where I could have actually been enjoying statistics. So if this is going to happen, as you say, at A levels, or even earlier on, that's probably a bad thing. But let's not, I mean, one view of machine learning from a statistician's point of view might be a good way of tricking people into learning statistics, right? I mean, by, if I was trying to tell my daughter, why statistics is exciting, or my wife, who hates it when I call myself a statistician, I would start with, well, let's understand how we make inferences about data, right? Isn't that fundamental to the sciences? Isn't that fundamental to how the brain works? Let's start to think about that. We have data, we need to, figure out something uncertain from something observed. And how do we do that? What's the mathematics of doing that? And I actually think it's fascinating. And it's very sad that, that sort of excitement can't be given to people at a much earlier age. So I sincerely hope that, a lot of thought does go into how it's taught.
There's a lot of historical accident there as to whether it's taught, whether we think of statistics as a piece of mathematics, science, or engineering. So in mathematics, the goal is to make rigorous statements. In science, did I say mathematics? In mathematics, the goal is to make rigorous statements. In science, the goal is to sort of understand things and to make interpretations, as Patrick said. And in engineering, the goal is to build stuff, right? So if you think about statistics as a tool that's helping you build a recommendation engine or build a data product, the definition of mission accomplished is quite different, and I think will be more exciting to young people. I say historical accident because in many cultures of statistics was thought of as a branch of mathematics, and particularly in the States, when the National Science Foundation was established, statistics was located within the Division of Mathematical Sciences, and that had, I'd claim, some very pathological consequences, including the fact that if you wanted to get funded as a statistician, you needed to show your bona fides as a mathematician because you were being funded by a branch of mathematics. And this is not just David Madigan, my colleague at Columbia, says he wishes that statistics would have grown up more a part of engineering because there's so many ways to use statistics for building things. Nonetheless, I think that's why you get this sort of heretical branch of statisticians like John Tukey and Leo Breiman sort of saying that statistics shouldn't be all about rigor. It should be about the primacy of the data, as Lehman put it in describing Tukey's work. And that's part of, you said earlier that there's nothing new under the sun. I mean, intellectually, a lot of what you read in data science reads a lot like what John Tukey was writing in 1962 in The Future of Data Analysis, or what Bill Cleveland was writing in 2001 when he proposed a new field called data science, or in Leo Breiman's any various exhortations for statisticians to spend more time with data and computation. One thing that is new under the sun is technology. So technology equals change. So intellectually, there's a foundation there among people as old as Tukey and Breiman, who certainly had their mathematical bona fides, but technology is constantly pushing us into new intellectual areas.
Yeah, I mean, it's no coincidence that Tukey invented the FFT, among other things, and coined the term bit. I mean, intellectual openness is I think, has always been a hallmark of successful statisticians. I think that the fundamental things that an understanding of statistics can contribute, and this goes back to the A-levels question, are about understanding uncertainty, frameworks for understanding uncertainty, reasoning under uncertainty, and frameworks for understanding and reasoning about variability. We choose to apply those mathematical frameworks, those mathematical constructs, to model things in the world or to build systems. But I think what I've seen when teaching undergraduates is that the hardest but the most rewarding thing to teach people is ways to think about reasoning under uncertainty, ways to think about understanding variability. Why is it that probability theory turns out to be a useful way to understand variation in data? Why is it that thinking about a population and a sample and a sampling distribution can give you insights, et cetera, et cetera? So I would love to see more of a focus earlier on these things, on the ways of thinking that I think are really at the core of modern and also of classical statistics. And I think sometimes that gets lost in the teaching of technical details or the hand cranking of calculations and so on and so forth. We do a much better job teaching people intuition about basic Riemann calculus than we do about helping people understand why a Z test is meaningful in a certain situation. And I think it would be great to see that begin to change. I don't know if it will, but I think that would also help us to understand where core statistics sits within this broader landscape that includes machine learning, for example, and all these kind of other things. So I think that just some thoughts on that.
I think we need people with both sorts of attitudes. We do need people who are prepared to take the data and build a neural network and so on, and rush in, if you like, and risk disasters. We need people who are adventurous and courageous, but we also need people who are conservative and cautious, so they can say the disaster has occurred because you didn't take into account selection bias, so clearly your results are going to be wrong and so on. We need both sides of this. I think a lot of the problems that we've heard, the maths A level and the earlier question, is because of the intellectual heritage of statistics. It grew up as a sort of mathematical discipline. It may, I personally, and I think everybody here, thinks it should have graduated beyond that now. It's just as much a computational discipline as a mathematical discipline. But that's where it all comes from. But I think we've heard, and this is right, that statisticians have a sort of reputation of being critical. And I think that's quite important, that in some sense we retain, if not the reputation, at least the ability to be critical. It would be nice if we could propagate that out into the community so that when people read the papers and read numbers and read claims made by politicians prior to elections and so on, they can look critically at those numbers and think, does this make sense? Could that possibly be true? I think that's an important attribute that statisticians have.
I think that critical attitude is really, really helpful in business as well as in stats. But I think the thing that people sometimes run up against is if a statistician says, no, you're doing that wrong, full stop, not actually what you should have done is. And I think if that became a more commonplace next thing, that would be very helpful. Because I think a lot of the time, certainly in the programming community, people are keen and interested in being educated, but they find walls where they don't necessarily need to be.
So not, no, you're doing that wrong, you idiot.
Yeah, exactly. Which is sometimes what happens, but you're doing that wrong, but if you read this or educate yourself about this topic, then that would help.
One possible source for optimism is the rise of data journalism and sites that do spend a lot of time saying, this was wrong, and here's how you might use Bayes' rule or infographics or a little bit of R code posted on GitHub or something that helps people empower their sort of critical literacy. Even if they're not going to master functional literacy and can do it themselves, they can at least have critical literacy to know when they're being lied to.
Yeah, those kinds of data journalism, sort of close readings of stats are fantastic, I think, in education.
No, I was just going to say, I mean, I think that's exactly why I was sort of pushing gently before for if we can convey to non-specialists enough about statistical reasoning to reveal some of its power, I think that's what drives a lot of the interestingness of things like data journalism, right? It's kind of rolling the situation or the idea around in your head and understanding like, oh, well, maybe there's sources of variation that I didn't think of, or maybe I observed the result that I observed purely due to chance, or maybe if I take the same data set and ask many, many questions of it, I will have inflated my chance of a false positive, and so on and so forth. Like, as you said, the functional mastery is not really, I think, that important unless you're determined to become a specialist. But the intellectual paradigms, the ways for thinking about variation and the ways for thinking about uncertainty, I think are very, very powerful, and that's what the discipline really has to offer up to the discussion, right? The broader discussion of all of these issues and the way that they arise in the modern world and in all of our lives.
Let's take another question from the floor.
Sheila Burt, Medical Research Council. I wonder if the panel might comment on whether they think that the opinion surveys prior to the UK election were found data or designed surveys.
I think I'm the one person here.
I don't know the answer, but I did notice a discussion about one pollster who didn't publish their results because it was an outlier, compared to all the other polls. And had they actually published those results, they would have been much closer to the actual outcome. So I don't know whether that, to take that at face value, but it's certainly an interesting conundrum for pollsters right now.
Yeah, I think there's always one post hoc after the fact who got it right. There are quite a few economists who predicted the financial crash in 2008 after the fact. There are many more. But I think what's particularly interesting about the failure of the polls is that they hadn't failed so dramatically in previous years, previous elections. So what was different about this one? It can't just be that people who are going to vote Conservative suddenly lied prior to this one, or whatever. So what was different about it? And it wasn't just the polls, but the YouGov system and so on. There are other things which went wrong as well. So it's a very interesting question, and I'm looking forward to finding out in future months what exactly went wrong.
Yeah, I think one of the tricky things to think about is correlatedness. You'd like to think that all the polls are somehow independent, but there are some linkages. I mean, in the way that people design their sampling mechanisms and so on and so forth. So there could be some things that explain the kind of systematic biases that were observed. There's also the kind of interacting effects of the fact that we now live in a world where there's kind of instant polling all the time, and surely the availability of that information feeds back into people's decisions about how to vote. So I think it's another example of, where, so there's two opportunities there where the fundamental assumptions that underlie basic polling are not satisfied, right? The idea that when you look across a bunch of different polls, if you weigh their evidence all equally, you're assuming essentially that they're independent, that they're not correlated. And then there's the fact that we don't take into account in polling the effect of previously published polls on how people are currently thinking, et cetera. So, but I think, as David said, it's a really interesting one because clearly there's something so rather systematic at work here, and maybe it'll cause people to think hard about what we might do differently, the next time around. It's going to be an interesting post-mortem, I think.
I think that statistical theory at least tells you that there is something wrong, substantially wrong, and the discussion of the panel shows the importance of survey design into the understanding, and therefore, without knowing how data are collected, one can know that there is something amiss, but not what is amiss.
Not what it is, yeah.
And those are essential statistical issues.
Yeah.
That's absolutely right. You can't just say, we'll look at the data. Actually, though, Sheila, as you know, in fact, the polls were all right, but the election was wrong.
Besides, life would be boring if it always came out like the polls. So at least we gained some excitement out of the whole thing.
Yeah, exactly. The surprise element was non-zero.
Why don't we do a poll now, actually? Who identifies in this room as a data scientist? Interesting. And a statistician? And a machine learning specialist?
We do more than one.
Yeah, I am. And none of the above. Interesting. Let's take another question.
Kevin McConway, Open University. This is partly picking up on something that Chris said earlier. What I was thinking about was, Roland kindly pointed out to us at the beginning that the Royal Statistical Society has been around for 180 years. And if you think about the early decades of that, there was probably nobody or hardly anybody whose job description said they were a statistician, but there was a discipline of statistics, a set of interests in statistics, and all that kind of thing. Now, let's put universities to one side because, as has been said, tenure lasts a long time. Going ahead maybe 25 years, do you think there will be people outside the academic sphere whose job description says they are a statistician? Or will there be people doing statistics who are actually described as data scientists, analysts, biometricians, whatever?
I think there will. I mean, this illustrates the breadth of statistics. There are thousands of government statisticians, and I'm sure they'll continue to be called statisticians.
Another question?
as a person that have gone to industry and basically built data science teams and recruited from both departments, I would like to emphasize a point that Zoubin made earlier, that in industry and lots of problems, 90% of it maybe is, concerns computing by and large, and maybe 10% is really statistics or machine learning. People coming from computing backgrounds that have taken maybe a course or two in machine learning or AI or stats, they usually have a much better chance of succeeding in being productive at workplaces than basically if you swap it, the statisticians that come and maybe have taken one course in programming. So I think, by and large, I think statistics have to, or programs have to start, computing and injecting computing into their curriculum from much earlier, because I think that is a way to succeed, at least in industry, as far as I can see.
Can I make a comment about that, which is, although I can understand that might be true from the point of view of recruiting, one issue is that sometimes recruiters at companies think of statistics or machine learning as sort of equivalent to skills like Java or something like that. So what are the skills that you have? It's Hadoop, Java, and machine learning or something. And it's not quite like that, right? Because you can't, you can gain a very basic understanding of these tools, which maybe is good enough to make you productive. But ultimately, to go beyond sort of downloading some software and running it, I think it's a very hard job, and that's why there's demand actually now for PhDs who have presumably several years of experience of actually thinking about statistical modeling and machine learning. So I can see what you're saying, but I'd like skills like statistics and machine learning not to be kind of placed at a comparable level to Java programming, let's say.
I think as the years go by and people start using the term with a little more nuance, you'll see people differentiating between data science, data engineering, data product, data DevOps, like the things you need to do to maintain and monitor a production data product are slightly different than developer operations for other types of software engineering. So I think you already see that now, that people are differentiating between data engineering and sort of the skills like MapReduce and the ability to deal with data at scale, as opposed to the data science, which, as Zoubin said, data science includes a set of skills like obtaining the data, building some models, which is sort of the fun tech nugget, and then interpreting the result in a way that other people understand. I
think it, having said that you don't want to mix things up, I think there is an argument for including some programming in those courses, not because it teaches you to program, but because it can help you fall in love with the stats.
No, I certainly didn't want to imply that I wouldn't want to mix things up. In fact, I think we should be mixing up like crazy. And I'd like to give an example of, I spent 10 years as a part-time faculty member at Carnegie Mellon University, and they're actually quite unique because they have a department of machine learning sitting in a school of computer science with 7 other departments. And the Department of Machine Learning sits essentially between their core computer science department and their statistics department. And the way they teach classes, and I was fortunate enough to teach a bit while I was there as well, is they get a computer scientist and a statistician co-teaching. Most of their postgraduate level modules are co-taught by people from these two disciplines. And although the two senior people, probably it's hopeless for them to really learn to communicate at the stage of their careers that they're at least the students get to watch the two senior people have debates about what the meaning is of something or other. So maybe the next generation can get both of those skills. And I think that's a great model, and we should be trying to emulate that sort of thing here.
Doesn't that argue that our gap is not hard skills, but communication skills in that case?
Yeah. I think I really agree with your point about injecting algorithmic thinking earlier into the curriculum. I think there's 2 interesting points here. The first is just that, as we've already heard, statistics can be rather conservative and rather slow to being willing to change its approach to curriculum design. And clearly we're paying a price for that. That's something that I think everyone around the table has agreed. The other really interesting intellectual point, though, is that it does go back in a way to part of statistical thinking. So in the classical paradigm, or the canon, or the orthodoxy, or whatever you want to think of it, one doesn't pollute one's thinking about the right model with any concerns about how you go about fitting that model, right? And holding these two separate, these two things separate, is a good way intellectually to protect yourself from kind of accidentally tuning to the data or ruling out certain models because they're a priori complicated or difficult to compute. So, you know, in the, let's say the early computer era, the 80s and maybe the beginning of the 90s, we had enough computational power that we could still live in a world where that old paradigm wasn't completely broken. We could sort of think really hard about the models, and then we could kind of scrape together enough computing power to fit them. And if you think about techniques like Monte Carlo methods or Markov chain Monte Carlo techniques, they're a real intellectual success of taking potentially very, very complicated gold standard models and fitting them in a way that's basically allows you not to care very much about computational cost. That's fine for the old paradigm where data sets were, you know, small and designed and relatively difficult to acquire and sort of precious. The thing is, in a world where we're dealing with lots of found data and where data rates are scaling, you know, faster than we've ever seen before, et cetera, we kind of can't afford anymore always to hold apart the ideas about model, you know, kind of model elicitation and the ideas about model fitting. I think instead we have to offer coherent intellectual frameworks to think about both of those things at the same time. So somebody like Mike Jordan, who's a leading machine learning expert, is starting, for example, to study those trade spaces explicitly. So you have a notion of computational efficiency, which is, you know, algorithmic runtime or memory usage. And then you have a notion of statistical efficiency, which is how much, you know, under a certain set of assumptions, how efficient are you at wringing the information out of your data? And one can imagine a smoothly sliding scale where one can begin to balance these things off against each other. And that's just not a paradigm that we've thought about in the past. And I think once we kind of get there, eventually this should help us to do what you recommended, which is to start injecting algorithmic understanding and algorithmic thinking earlier into the curriculum. At the expense of what, I don't yet know. We can't simply add things, we also have to remove things. But that's going to be another big challenge for kind of data science curricular design, if you like.
Of course, Leo Broman has written this rather famous paper called The Two Cultures, talking about algorithmic thinking versus sort of inferential thinking.
One curriculum, so we tried to do this at Columbia with a certification in machine learning, a certification in data science rather, that has 4 pillars: probability and statistics, algorithms for data science, machine learning for data science, and a class called exploratory data analysis and visualization. So by teaching the algorithms at the same time they learn probability, statistics, and machine learning, which even if they're subsets of each other, I think the definition of machine learning, definition of mission accomplished in machine learning is often different than the definition of mission accomplished in statistics. By teaching the algorithms at the same time as they're learning the prob stats, I think that's one way of trying to help people see both at the same time.
Another question over here.
Hitan Shah, Exec Director at the Royal Statistical Society. The RSS has been around for a long time, as you've heard, where in a space where, as you've described, the profession of statistics is changing, and then lots of disciplines which are on the penumbra of statistics are also changing. What do you see as the role for a body such as the RSS? What could we most usefully do to take this whole agenda forward?
I'm looking at Switzer.
I think from my point of view as somewhat of an outsider, I think attract outsiders, because there's a huge appetite to learn the things that people at the RSS know, but it's is slightly too unapproachable from many people's perspective at the moment. I think there's huge appetite to understand the knowledge that you guys already have, and you could be very important and much more known and revered than you are, which would be nice, I'm sure.
Yeah. We're open to all comers. I mean, you don't have to have a profession, qualification in statistics to be a member of the society.
You just have to be interested in it, and of course, everybody in this room clearly is. So, yeah. But I think that's exactly, you hit the nail on the head, and it was reflected in some of the earlier questions about statistics being, it's as if, at least some of the ways it's taught, it's as if they wanted to make it as difficult as possible. You've got to cope with all these mathematical things, all these distributions, rather than right at the start discovering the joy of statistics, because you're discovering things in nature, you're discovering things in data. That's really the way it should be taught. And I think, that's what the Royal Statistical Society has to do, and it's been trying to do this, I know, to communicate to people, to the public, that statistics is about discovery. That's really it.
I'm going to make a controversial point. So, from my perspective as a non-statistician, I found classical statistics very difficult and very unintuitive, and I find Bayesian statistics just like common sense. So, this is a controversial. Yeah. Well, I don't want to push any sort of agenda, because I know it's a very contentious point, and I think the field of statistics has gotten over the great debates and sort of built peaceful coexistence now. But, at a very early stage, I think one could teach simple ideas from Bayesian statistics and then teach classical statistics later as a more advanced topic. And people might find it much more intuitive. And they might then really enjoy doing the classical statistics after they've learned Bayesian statistics. So that's just my 2 cents.
Rather than weigh in between the space between frequentists and Bayesians, particularly since we're across the street from Reverend Bayes' grave, one white space is between the timescale of industry and the timescale of academia. So one thing that I think a professional society can do is to encourage academia to speed up and to encourage industry to slow down. And, like data science, if you want to hire a data scientist, that shouldn't be a meaningless phrase, right? And this is Martin's original point when he introduced the panel, is the terms should mean something. At the same time, it's not necessarily good for the species for everyone in academia to think that the definition of their field is whatever their PhD advisor did. That doesn't really get the species to move forward as the world changes. So a professional society, I think, can somehow be a good bridge in the timescales between those two parties.
Thanks, Chris. We have a question on Twitter. Okay. So I'll let you answer if you're here. Is Rob McKinney here? Oh, excellent. Could you ask your question?
You tweeted it for
one of the questions I was going to ask actually has been answered, which was, how do we balance an ability to apply the most sophisticated sort of statistical methods against the need to collect loads and loads of data, which everyone seems to want to do at the moment. And in my experience, you collect a lot of data, and as Zoubin said, our sort of role as a statistician is very, very small, and it gets kind of more simplified as we have more data, because we struggle to do it. We struggle to do anything in real time. I guess my question now would be, how do we then encourage kind of academic, sophisticated algorithms out of academia and into industry, which I guess follows on from Chris's point?
Well, industry people will do whatever it takes to win. So, I mean, if your company is using deep learning and is able to do image processing and image recognition faster than another company, you will do it, and you will find and hire the people who know how to do it. So I don't think industry is slow to take up the methods that work.
I guess you'd need to be aware of deep learning in order to do that.
Yeah, although in spring of 2015, there doesn't seem to be a big information gap between what's happening in machine learning departments and Google and Facebook are, rapidly getting in there and buying them, but before they've even defended their PhDs, right? They're now hiring them.
But I guess other than Google and Facebook, in 2011, let's say, was your typical startup know about deep learning? Question over here. Oh, we're running out of time. I understand. The round off, I get it. The hand gestures. We're running out of time, everyone. So, do we have time for one more question, Bennett? Yeah, one last question, please.
Hello. Well, my background is in ecology. I've been working in data science for the last couple of years, and it's a very interesting transition. So we're discussing a lot about the data part of data science, but not so much about the science part. So I would like the panel to comment about the science part for the next generation training for the education and in the universities, because I'm finding now with my colleagues and other people that they know a lot about the statistical models, they know about the solution, the technical solution, Hadoop, etc. But when it comes about asking the question, asking those whys, they sometimes fall short. So I just want to hear your comments about this.
Yeah, I think it's a really interesting point, and it's something that we probably haven't touched on as much in the discussion this evening as we might have. I think there does need to be like a kind of service component to the way that we think about data science, and a way to move smoothly between the spectrum of core methodological expert and core application domain expert. And it's a big open challenge to figure out how to get these people to talk to each other. I think, one argument would be that you provide a pathway to entry for people at the master's level who have done a first degree in a scientific, or in an application domain, and you teach them as much as you think they need to know about data science to interface. There's another approach that says that you take core data scientists, people, and core application experts, and you lock them in the same room together until they figure out how to talk to each other, right? I think it's not clear yet what the answer is, but what is clear is there are always, because of technology, we are in a world where there are always going to be scientists or application domain experts who have questions that they need to answer, and the size and scale of the data sets is just getting in the way. So part of understanding data science more broadly is figuring out what does the kind of service, the intellectual service model look like for that paradigm. And I don't have an answer, but I can tell you when we think about our Big Data Institute and how we should provide education at the master's level or continuing education at the executive level, these are the kind of things we think about. I think it's going to take a few years for it to shake out. Right now, people are running lots of different educational models to overcome this problem, and I don't think it's clear that there's one solution winning out over others, at least not yet. Others may have experiences to share. I don't know.
Anyone else?
Just a comment. I think to use a phrase that Chris used earlier, this whole discussion has really been about data technology, about how we bring tools which we apply to data. So we're in some sense engineering rather than talking about science, the invention of new tools to analyze data.
I think it's interesting. I think you were thinking about a different dimension of communication from what I'd expect as well. So you said make the application scientists and the data scientists talk to each other. Actually, I think the thing that I find is most often a gap is data scientists talking to the business and actually elucidating what the actual problem is they're supposed to solve, and making friends with people to find out where the data is and why it might be hidden and what the problems might be, and digging it out and communicating results back, especially if they disagree with somebody important's opinion, which can often kill your work dead. So that side of communication is, I don't know that you can teach it in an academic context, but I think it's a critical component of someone actually being a good data scientist.
Yeah, it's a great point.
Probably a good statistician also, realistically.
Yeah, and that is part of how we train statisticians. So, for example, at Harvard we did it by forcing people to do a cognate study during their PhD, which is a separate medium-term project with an entirely different set of people in an entirely different application domain. So you're kind of building the statistician's skill set, to be a communicator, to understand how to work with data stakeholders and so on and so forth. So I actually think that's something that we can apply in a master's context. I mean, it's, sometimes you think of it as consulting hours or a help desk or whatever you call it. Master students are very well primed to do that, but it's not really appropriate as appropriate for PhD students and faculty. Academic staff don't want to get engaged unless there's a lot more intellectual interestingness. But for master students, it's great because it teaches them some of these skills that you're talking about, and it gives them more experience points to kind of take into their job search afterwards. So that's something I think that we can do to address the concern that you're raising.
Yeah, I think that's actually a very strong historical tradition in statistics, is the ability to work with somebody from a different community, for example, natural scientists, and reframe their problem using careful thinking and a type of thinking that spans many problems, and solving their problems with data. So, for example, the skills of experimental design are, show up in many different fields, right? As we're seeing in polling or Facebook making claims about their, anyways. Experimental design would be good in many different fields, and statistics has historically trained people in the ability to work with people from a different discipline, either natural scientists or business owners or people who don't speak calculus or whatever they may be. I do think it's no accident that the people that I think of, at least, as progenitors of data science as an intellectual tradition, like Tukey and Bryman, spend a lot of their time consulting. So Tukey and Bryman came from like a very high church school of mathematics, and then sort of left the high church and went out and walked in the desert and worked with real people, who had real problems and real data. And I think it really informed their thinking around exploratory data analysis, data visualization, CART and random forest and every other trick that Leo gave us. So I do think that actually statistics has a strong intellectual tradition of empowering people from a different community, whether it's the natural sciences or business people, by learning to culture broker between the demands of the person and the data that they have.
And, I think it could be used as a great recruitment ploy into statistics. Come do statistics because you get to work with all of these different kinds of people and solve all sorts of interesting problems.
You get to play in everybody's backyard,
yeah,
as
exactly.
John Tukey said.
Yeah, and it's great. It's what makes it fun.
Okay, I think we should wrap up. We're going to hear a few words from John Pullinger, the UK National Statistician, before we close.
Okay, thank you very much, panel, and thanks to everyone who's contributed to this debate. I was asked at the outset to try and do a summary, which is a bit of a challenge.
I saw your sheet.
I'll kind of have a go. I've been scribbling in a manic way throughout the evening. The first one, I think, from the hands up when people were asked to kind of show their affiliation. I think that demonstrates that what we want to do here as a society is welcome people. We even welcome the accidental statisticians, even if they come and try and stir up old debates and get us going again. This kind of stuff works by welcoming everyone into the room. Now, I was thinking as the debate went on that the RSS started when centuries of expertise were being confronted by new methods of data analysis. And I was reminded that one of the 4 people who set up the rules of the society at its very founding moment was Charles Babbage, who had got kind of fed up with the fact that human calculations were fraught with error, so we had to invent some kind of machine to make it better. And we've always been partners in this endeavour. And as you look through the history of the society, our first female member was Florence Nightingale. She wasn't in an academic background, she was confronting the world with solutions to problems that the world was unable to see without good analysis, good data, good visualization, all the things we've talked about now. So the statistical profession that I know and the people on that board are mainly in the business of making the world a better place, whether it be in medicine, economics or politics. We've got 2 prime ministers on there. We have to work on the next one. What do you think, David? But we are now at the stage where today's revolution, as Patrick said, is a once-in-a-lifetime opportunity to change the paradigm. And really, we have the chance to grasp that. But also, as he said, be humble enough to recognise there's not all that much new under the sun. So my summary of tonight kind of looks at how we might tackle the demand side of that problem and the supply side of that problem. Now, on the demand side, we've heard some fabulous examples tonight about, as Francine described, new emerging fields of problems to be solved. David talked about a whole range of public policy questions. Zoubin talked about lots of commercial opportunities to get value out of data. It's there for us to grasp if only we get into the decision-making space to kind of help make those changes. The other side of the demand side of the problem is to educate the people who would actually consume the data. And we've had a lot of that in this discussion today. And Chris's phrase that I started with, when you confront centuries of expertise with data, it's painful and they don't like it. He talked about the journey of biology and journalism, but at the end there was a very nice phrase: if we start seeing ourselves as consultants, we can reframe the problem in a way that actually helps them with their decision making. And then we're in the right zone. So we've got some problems, we've educated the problem solvers in the fact that we have some solutions. But then we need to deal with the supply side. And I picked up 4 themes today on the supply side. The first one is data. There's lots of it, and we're really only just beginning. We didn't get into this debate at all about what happens next. But we all know in this room that this is just starting. The scale and the complexity and the opportunity of data is going to ramp up very, very fast. Not just year by year, but month by month, the change is accelerating. But data, you have to kind of care about what it is and where it comes from. As David said, all data sets have problems. N equals all is kind of seductive, but completely driving us down the wrong road. We have to care about data and making sure we get it right. We have to care, secondly, about method. Patrick talked about methodology and looking at the behaviour of large networks. Zoubin talked about how machine learning is discovering stats. There's a new methodology at this boundary that we need to really enhance and develop. And universities are coming through a little bit of a bad time, I think, in some of the discussion today, but it's in our universities that kind of deep thinking is going to take place. I don't really care whether it's in a statistics department or a computing department or any other department. There's some deep thought that needs to go into this stuff to discover the new methods that would unleash the potential. Third of 4 is the technology. As Francine said, so much more is possible now, but that is changing fast, and we need to get to grips with what the meaning of those changes are and embrace people at the frontier of that. And then finally, and I'll spend a little bit more time on this, about skills, which really did dominate this debate, and I think it's worth attention. Now, so an old guy like me who learned his statistics in the 70s, it feels a bit like Back to the Future. We didn't have packages in those days, we had to do coding in order to do any statistics at all. So this all seems kind of slightly weird to me. So I've gone through this strange phase of 30 odd years, and suddenly we're all coders again. But that's great. We should really go with it. It's brilliant. But what have I got here? What have I got here? Some good things here. So, the Back to the Future skill set. Francine says, we need people who are better than programmers with stats and better than stats with programming. But she also said, when you try to teach programmers some stats, it can be scary. And my laugh-o-meter, that got the biggest laugh of the evening. So we've got to really grasp how we teach people these skills on both sides, and even more at the kind of intersection. And a lot of the questioners were highlighting just how poorly served we are currently in our schools and universities by making these most exciting subjects the most boring ones. And if there's one thing we can all take away from this meeting, to be the campaigners in the education curriculums, in university departments, and in businesses, the kind of training that we give to our staff in our organisations, to really embrace this stuff and make it fun and make it interesting, make it the course that everybody wants to be on. So, what are these skills? Well, a lot of them are new, but some are really quite old bottles for this society. And Francine described it, pushing the basics. And they're all about letting us make sense of the world from the data we've got. Now, David gave a robust defence of data scepticism, which I thoroughly approve of. That is the kind of archetype of the statistician. But it's not about being a naysayer, and I thought that discussion there was a really, really nice one. It's about always being curious about data, and curiosity is a really interesting attribute. It draws us in rather than puts us off. But data scepticism has to be at the heart of our skill set. Leading from that, another statistician old staple, which hasn't had too much going in the discussion today, is bias. Every data set is biased. And unless you start challenging the sources that we've got, so which bit of the entire population are we really getting to grips with here, and what's going on in the bit we can't see, the kind of dark matter of data, that's where we really get creativity from statisticians and computer scientists getting together. Similarly, with the other old staple of uncertainty, precision, variability. This is at the heart of what we've learned in all those dull courses that some of us managed not to sleep through. But they are the heart of the statistical discipline that we have to celebrate and use and put to the service of the great data sets we're now creating. Otherwise, we will misdirect ourselves in what we can discover from them. And fundamentally, our discipline is about discerning which patterns have some meaning and which are just the kind of random fluctuations of a rather crazy universe. So let's bring all of our skills together, let's enhance them, let's celebrate them wherever we can. Because data science and statistics, we are in the same world. Let's work together to make the world a better place. Thank you all very much indeed.